Yeah, okay. So, good evening, everyone. I am Shivani Dhok, and I welcome you all to the week 9 tutorial of the course of Introduction to Wireless and Cellular Communication Systems. By unmuting yourself because the chat box might not be visible to me throughout the lecture. And like every week, this week's tutorial will be divided into two parts. First, we'll have recap of week 9 content, followed by the questions which are related to the recap of week 9 content. Before starting, I apologize because I was not able to take lectures on the regular timing, which is Friday 6 to 8 p.m. due to some meetings on in this week and in the previous week. But in coming uh, 3 weeks, I'll have it scheduled on the regular Friday 6 to 8 slot. Okay, so let's start with the recap of week 9 content. So week 9, we started by revisiting or revising the content of last few weeks, and after that we went on to discuss and revisit the concepts of capacity. For example, the ergodic capacity voltage. Just for as a recap, what is ergodic capacity? So ergodic capacity, by definition, it is given by integral capacity. So this is capacity, Shannon's capacity, which is evaluated at the SNR, instantaneous SNR, into the PDF of this SNR d gamma. This is 0 to infinity. It's a SNR is a positive quantity.
Hello, hello.
Hello. Yeah, sorry, there is some issue today with my internet. 1 minute. Yeah, yeah.
Yeah, yeah.
I,
I,
yeah, I get it. My screen is not visible. Just 1 minute. I don't know. I'm not able to share it. Can you see my screen now?
Can you see my screen now? Yes, ma'am.
Can you see my screen? Hello?
Hello?
Yes, madam. Your screen is visible, ma'am.
Yeah, yeah, thanks. 1 minute. The screen is visible. I'm audible now. So let me start.
Hello? Hello?
Madam, your voice is not audible. Madam, your voice is not audible.
Am I audible now?
Ah, yes, madam. Now it is clear.
Yeah, okay. Yeah, thanks. Okay. So we were looking at capacity with outage. Let me see. across different SNRs. For example, if we know that there are multiple SNRs that are available to us across time, then is it possible to design a code, design a power allocation scheme wherein we change our transmit powers or our SNRs, transmit powers based on what channel condition we see? And we saw a very interesting algorithm which is known as the water filling algorithm. And this water filling algorithm says that you allocate more power to good channels. So this water filling algorithm gives you optimal power allocation. And the goal of this is it wants to maximize your ergodic capacity and this maximization is with respect to your powers, let's say P of gammas, or yeah, leave it, such that your average power constraint is satisfied. And what is your average power constraint? Your average power constraint is nothing but integral 0 to infinity P of gamma. P of gamma here is not probability, here P indicates the power, into F gamma of gamma should be less than or equal to P bar, where this P bar is your average power constraint or maximum average power. So basically, this is your average power constraint. And based on this, and by constructing the Lagrange and all those things, we found out how to maximize the power, how to maximize the ergodic capacity by optimally allocating the power. And we saw a very interesting thing, which is something known as water filling effect. So if we plot 1 by SNR, and if we have SNR here, then there is some threshold which is gamma naught. And if my SNRs vary something like this, okay, wait. Yeah, so we have something like this, gamma and 1 by gamma. So what we say, if my 1 by gamma is greater than this gamma naught, we are not going to allocate any power to it. But if my SNR, this is 1 by gamma naught. Yeah, if SNR 1 by gamma is less than 1 by gamma naught, then we will allocate this much amount of power. So this is like this line here, this red line here can be considered as a bowl here, in which we want to fill the water, and this is the maximum allowed water level. Now what will happen when you fill the water till this particular level? A higher amount of water will be available in this region where the depth is higher, and a lower amount of power will be allocated in this region where the depth is lower. So this is something that we see every day when we are trying to fill water in some vessel. That's why this particular algorithm is referred to famously as water filling algorithm. After that, we looked at another technique which is known as channel inversion. So in channel inversion, we said we want to see the capacity which is equal to your, at every SNR, we want to see a capacity which is equivalent to an AWG in channel subject to a power constraint. So basically, our capacity for a given SNR, that is C of gamma, is basically given by log to the base 2 1 plus P of gamma by gamma, P bar into gamma. And we want this thing to be equal to some sigma. So that gives us P of gamma by P bar to be equal to sigma by gamma. And now we want to find this sigma such that average power constraint is satisfied. So this is channel inversion. And when we solved this, we saw that the sigma turned out to be 1 over expectation of 1 by gamma. Then we looked at another thing which is known as the truncated channel inversion. Now this truncated channel inversion is okay. So this truncated channel inversion is, again, we want to get something like this. We still want to have want to see a capacity which is similar to the AWGN formula, but for SNRs which are higher than some threshold. So basically, for truncated channel inversions, we are allowing for some outage. So the sigma now will be obtained by 1 over expectation of gamma naught 1 by gamma. And finally, we started looking at an important concept of CDMA. So this it was just a little bit introduction to the concept of CDMA. Of course, we'll be looking at the CDMA thing in a much greater detail in this particular week, that is week 10. Okay. So in CDMA, what we said was we want to send some signal, some symbol which is SI. This is the symbol which we want to transmit. Okay, and to do that, what we do generally is we transmit a signal, a waveform, which is given by u of t, which is equal to SI into under root EB, where EB is your symbol energy, into G of t, where this thing G of t is the pulse shaping filter. Pulse shaping signal. Okay, and what we are looking at is something known as the direct sequence spread signal. Which is basically your DSSS. And in this, what we say is the pulse shaping filter G of t is basically given by Q equal to 1 to capital Q, C of Q, GC of t minus Q times TC. Here, this Q, capital Q, is basically your spread factor or spreading factor. Then the C of Q is your spreading sequence. And this GC of t is basically 1 over under root TS for 0 less than or equal to t less than or equal to capital TC. And this thing has its Fourier transform, which is given by under root TS TC sinc of FTC to e power minus j 2 pi FTC. So basically, this signal has a null at 1 over TC, and this Q times TC is basically your TS, where TS is your symbol duration. And this TC is referred as your chip duration. Okay. So this was just an introduction that was given to you to CDMA in this particular week, in the ninth week. However, we are going to look at this CDMA thing in a much more detail in the coming weeks. Yeah. Any questions till now? So that was all about the recap. If you have any questions, then please let me know. Okay. If there are no questions, then let me move on to the next first question that I have planned to cover today. Okay, so this particular question I had already covered in last week, but I had made a calculation mistake while doing things. So while calculating capacity, instead of doing log 1 plus SNR, I by mistake calculated log of SNR. So that was a blunder from my end. So this particular question I'm revisiting, and this is a correction to previous week's question. And it will also set a stage to figure out a few answers of the subsequent questions also. Okay, so let's start. So what is given to us is, consider a channel with 40 kilohertz of bandwidth. So this is the bandwidth that is given to us, and with the following SNRs, and this SNR is given by gamma I, which is equal to alpha I squared into capital gamma, where this capital gamma is given by 15 dB. And linear scale, this is basically 10 to the power 15 by 10, which is nothing but 10 to the power 1 by 5. Okay, so therefore, which means that this gamma i's are given by alpha I square into this capital gamma, which is equal to 10 to the power 1.5. So using this formula here, using this formula here, we'll now find out the SNRs for this given alpha i's. So what we need to do, we want gamma I, which is equal to alpha I square into 10 to the power 1.5. Yeah. So the first one here, yeah, okay. So the first alpha here is basically 0.1. So we have 0.1 squared multiplied by 10 to the power 1.5, which comes out to be equal to 0.3162. Then we have 0.2. So this will be 0.2 square into 10 to the power 1.5, and this thing comes out to be equal to 1.2649. Then we have 0.5 as alpha 3. So gamma 3 will be 0.5 square into 10 to the power 1.5, and this, if we solve using calculators, comes out to be equal to 7.9051. Then we have 1.5. So this thing will be 1.5 square multiplied by 10 to the power 1.5, and this comes out to be equal to 71.1512. And finally we have 2. So this will be alpha square, that is 2 square multiplied by 10 to the power 1.5, and this thing comes out to be equal to 126.4911. Now what is asked to us? We want to find out the ergodic capacity. I'll just make a small change of notation here just to have consistency. I'll just write it as probability. Yeah. So this ergodic capacity say C, it is given by summation I equal to 1 to, we have how many SNRs? We have 5 SNRs. So 1 to 5 C of gamma I into probability of gamma I. Now the C of gamma I is what? The C of gamma I is given by your bandwidth multiplied by log of 1 plus gamma I to the base 2 into probability of gamma I. What is the value of bandwidth given to us? Bandwidth is 40 kilohertz. Okay. So therefore, your bandwidth is 40 kilohertz. Therefore, this outage capacity with outage comes out to be equal to 40 kilohertz multiplied by summation I equal to 1 to 5 log of 1 plus gamma I into probability of gamma I. This is given by 40 kilohertz into, now we'll substitute these things one by one. So probability of log of 1 plus gamma 1. Gamma 1 is 0.3162 into probability of gamma 1, which is basically 0.3, plus log of 1 plus gamma 2. Gamma 2 is 1.2649 with probability 0.5. So this is 1 plus 1.2649 into probability 0.5 plus you have log of 1 plus gamma 3. Gamma 3 is 7.9051 multiplied by probability is 0.1 plus log to the base 2 1 plus gamma 4 is 71.1512 and its probability is 0.09 plus you have the final one, that is 126.4911 and its probability is 0.01. So you have log of 1 plus 126.4911 into 0.01, and this thing here comes out to be equal to 40 kilohertz multiplied by 1.6496, and this, if you multiply by 40, this comes out to be equal to 65.985 kilobits per second. So this is your ergodic capacity. Any questions till this point? Any questions? Okay.
No, madam.
Yeah. Okay. If there are no questions, then let me move on to the next question. Okay, so what is given to us in this question is, or rather, what is asked to us in this question is for the data given in question 1, find the optimal power allocation. Okay, so for this, we'll be using the discussed water filling algorithm. Okay, okay. Now, before starting, what I'll do is I'll just write down or reproduce those gammas and probability of gammas. So we have gamma I and probability of gamma I. So my gamma 1 was 0.3162. Then I had 1.2649, 7.9051, 71.1512, and 126.4911. And the corresponding probabilities are given by 0.3, 0.5, 0.1, 0.09, and 0.01. Okay. Yeah. So these are the things that we have. Now in water filling, how do we proceed? So we had seen in the lecture that first we need to figure out our average power constraint. So the average power constraint is basically given by I equal to 1 to 5, 1 over gamma naught minus 1 over gamma I into probability of gamma I to be less than or equal to 1. Okay, so this is the power constraint, and it will be maximized if we have equality. So this should be equal to 1. Okay, now what we need to do is we want to figure out, yeah, and the power, the optimal power it is given by P of gamma by P bar. This is PR. This is probability. Yeah, is given by 1 over gamma naught minus 1 over gamma I, which means that we need to first find out this gamma naught. Okay, we first need to find out this gamma naught, and then we need to substitute these into the power in the power expression, and this gamma naught will be found out. This will be obtained using the average power constraint. Okay, so let's do it. Let me just take this again on the next page. I want to. Okay, so now, so when we are writing this constraint, the inherent assumption is your gamma naught is less than your gamma I for all I in your range of interest. Okay, so now what we do is we first start with all the available SNRs and then find out whether this gamma naught that we have obtained satisfies this condition. If it does not satisfy this condition, so for whatever values of SNRs it is not satisfying, we'll shut off those particular SNRs and then revisit the same condition, same average power condition with the remaining SNRs and figure out the new gamma naught. And this process will be done till the time you see a gamma naught which satisfies this particular condition for the remaining SNRs whatever are available. Okay, so let's start with all the SNRs. So step 1 is assume gamma naught is less than gamma I for I in 1, 2, 3, 4 and 5. Okay, in that situation, this particular condition constraint that we have is basically summation I equal to 1 to gamma I, 1 to 5 and into 1 minus gamma naught minus 1 by gamma I into probability of gamma I. This has to be equal to 1. Now right hand side becomes 1, left hand side becomes 1 over gamma naught into I equal to 1 to 5. Then we have probability of gamma I minus summation I equal to 1 to 5 probability of gamma I by gamma I, which is equal to 1. Okay, now let us substitute things here. So this since we are considering all the available powers, this particular thing, that is summation of all the probabilities, comes out to be equal to 1. So this thing here is basically equal to 1. So now what we have is 1 over gamma naught minus summation I equal to, okay, rather than we'll just directly write them. Probability of gamma 1 is 0.3 upon 0.3162 plus you have 0.5 upon 1.2649 plus probability of gamma 3 is 0.1 divided by gamma 3, that is 7.9051, plus probability of gamma 4, that is 0.009 divided by gamma 4, that is 71.1512, plus you have probability of gamma 5, 0.01 divided by, you have its value, that is 126.4911 equal to 1. Now if you simplify this, it comes out to be equal to 1 over gamma naught minus 1.3580, which is equal to 1. So therefore 1 over gamma naught is equal to 1 plus 1.3580, which means that this gamma naught comes out to be equal to 1 upon 1 plus 1.3580, which comes out to be equal to 0.3162, 0.4241. Now this 0.4241, is it less than all the SNRs available to us? No. So if you observe gamma 1 is 0.3162. So this gamma naught is basically greater than my gamma 1, but it is less than gamma 2. So we are fine with it. So gamma 2, gamma 3, gamma 4, gamma 5 can be included in the subsequent step, but gamma 1 need to be excluded. So this thing is greater than gamma 1, which means we want to exclude gamma 1. So we are not going to allocate any power in gamma 1. Why? So if you again go back and see the Waterfilling algorithm, this gamma 1 is lying in this region. So if it is lying above this, okay, so what we are having is this gamma naught is greater than gamma 1, which means that 1 over gamma naught is less than 1 over gamma 1. So this gamma 1 basically lies in this region. So no power will be allocated to all the SNRs which lie in this particular region. and therefore the power allocated to this is 0. Now we want to figure out what values of SNRs lie in this region. That we will be doing by figuring out our gamma naught. Okay, so now we will exclude gamma 1 and again we'll revisit the power constraint. So now revisiting power constraint with gamma 1 excluded. Okay, so what do we have now? Therefore, the new constraint is summation I equal to 2 to 5 1 by gamma naught minus 1 by gamma I into probability of gamma I should be equal to 1. Okay, so now let us do that. So therefore this left hand side becomes 1 over gamma naught summation I equal to 2 to 5 into probability of gamma I minus summation I equal to 2 to 5 probability of gamma I divided by gamma I equal to 1. So now let us substitute those things. 1 over gamma naught. Then we have inside the bracket, we are now interested in these SNRs. This one is excluded. So this probability will be 0.5 plus 0.1 plus 0.09 plus 0.01 minus, we'll have the probability 0.5 divided by the SNR, that is 1.2649 plus the probability, that is 0.1 upon gamma 3, that is 7.9051 plus probability of gamma 4 0.09 divided by 71.1512 plus you have your gamma 5, its probability is 0.01 divided by 126.4911 and this has to be equal to 1. So this thing comes out to be equal to 1 over gamma naught multiplied by this thing here is 0.7 minus this thing here comes out to be equal to 0.4093 equal to 1, which implies that my gamma naught is equal to, what I'm doing is I'm shifting this side, so that will give me 1 plus 0.4093 and I'll divide it by 0.7 and take an inverse. So therefore in numerator I'll have 0.7. So now this comes out to be equal to 0.4967. Now if you see the 0.4967, is it less than gamma 2, gamma 3, gamma 4 and gamma 5? Yeah, gamma 2 is 1.2649, which is pretty much higher compared to your gamma naught. So therefore this gamma naught, this is higher than, so this is less than your gamma 2, gamma 3, gamma 4 and gamma 5, which means that gamma naught is equal to 0.4967 is a valid choice. Is it clear? Okay, so now if once we have gamma naught, what we need to do? We need to now use this formula, optimal power, that is 1 upon gamma naught minus gamma I. This is half written. This is plus with this notation. X plus is basically max of x comma 0. So it does not allow negative values. Negative values are shut down to 0. Okay. Okay. So now let us find out the power. So the optimal power or optimal powers will be P gamma 1 of P bar will be equal to what? Your gamma naught is greater than your um, gamma 1. So therefore 1 by gamma naught minus 1 by gamma 1 is negative. So this is basically 0. We have already excluded this SNR. So we are not going to transmit over this SNR. So therefore the power for that particular SNR is 0. Now this power at gamma 2 by P bar is given by 1 by gamma naught minus 1 by gamma 2. Our gamma naught is 0.4967. So this is 1 upon 0.4967 minus 1 over gamma 2, that is 1.2649. And if you solve this, this comes out to be equal to 1.5674. Similarly, we can do it for gamma 3. For this, the power will be given by 1 by gamma naught minus 1 by gamma 3. Okay. Yeah. Okay. So this comes out to be equal to 1 over 0.4967 minus 1 over gamma 3. Gamma 3 is 71.1512. Sorry, 7.9051. And this comes out to be equal to 2.2315. Then we have power for fourth SNR, that is 1 by gamma naught minus 1 by gamma 4. This comes out to be equal to 1 over 0.4967 minus 1 over gamma 4. Gamma 4 is 71.1512. This comes out to be equal to 2.3439. And finally, we have power at gamma 5, which is equal to 1 over gamma naught minus 1 over gamma 5, which is equal to 1 over 0.4967 minus 1 over, we have 126.4911. And this comes out to be equal to 2.3501. So these are the powers which are normalized by your average power. So if you want to get the actual powers, you just have to multiply all of these equations by the given average power. Right now, these are normalized by your average power. Any questions in this process? Is it clear?
Yes, ma'am.
Sorry?
Yes, ma'am. Yes, ma'am.
Yeah, okay, thanks. Okay. If it is clear, then let me move on to the next question. So the next question here says that what rate does the optimal power allocation offer? So now this for optimal power allocation, this capacity. So I'll write this as C opt, which is basically the capacity or your ergodic capacity, to be specific, with optimal power allocation. Okay, so this will be basically given by bandwidth times summation I equal to 1 to 2 to 5. This is starting from 2 because gamma 1 is excluded. You have probability of gamma I into log of 1 plus p of gamma I divided by gamma divided by p bar into gamma I. Okay, so now let us substitute this p of gamma I by p bar with this equation, this particular equation. So what do we get? Bandwidth summation I equal to 2 to 5, probability of gamma I log of, this is to the base 2, 1 plus, this is 1 over gamma naught minus 1 over gamma I into gamma I so this is equal to b times summation I equal to 2 to 5, probability of gamma I log to the base 2, 1 plus gamma I by gamma naught minus gamma I by gamma I, which is equal to 1. This gets cancelled. So at the end we get C with optimal ergodic capacity with optimal power allocation as bandwidth into I equal to 2 to 5, probability of gamma I into log of gamma I by gamma naught. So now let us substitute these things. So again we are interested only in these values, and gamma naught was 0.4967 and bandwidth was 40 kilohertz. So 40 kilohertz into probability of gamma 2, that is 0.5 into log to the base 2, 1.2649 divided by 0. Just a minute. Yeah, 4967. So this is, just a minute, 0.4967. Previous one was, yeah, 0.4967 plus you have 0.1 into log to the base 2, 7.9051 divided by 0.4967 plus you have 0.09 into log to the base 2, 71.1512 divided by 0.4967 and last 0.01 into log of 126.4911 divided by 0.01. Okay, so I'll just remove this thing from here. So what we have is,
Excuse me, ma'am.
what, yeah,
Ma'am, in last divided by 0.4967, na?
sorry, yeah, sorry, you're correct. Okay, so now this thing here comes out to be equal to 1.2649 divided by, yeah, Okay, so the first thing here comes out to be equal to 0.6743 plus you have 7 point this comes out to be equal to 0.3992 plus 0.09 into you have 71.1512. This comes out to be equal to 0.6446 plus you have 0.01, that is probability, into 126.4911. Yeah, this comes out to be equal to 0.0799. So this comes out to be equal to 40 kilohertz into 0.6743 plus. So this comes out to be equal to 1.798 798, and if I multiply it by the bandwidth, it comes out to be equal to 71.92 kilobits per second. Okay, and what was the ergodic capacity we had found out when we are having equal allocation of powers? So that we had obtained as 65.985. So this is greater than, whatever we have obtained is greater than, this thing is greater than the ergodic capacity with equal power allocation. Is it clear? Any questions? Okay, if there are no questions, then let me move on to the next question. Okay, so this question says that what is the capacity that you get with channel inversion? Okay, so in channel inversion, what do we want? So let us revisit that thing. So this capacity with channel inversion is given by B times log to the base 2 1 plus you have your P of gamma by P bar into gamma, and this thing, this P of gamma upon P bar of gamma should be equal to sigma, which means that P gamma by P bar should be equal to sigma by gamma. Okay, so the C of channel inversion is B times, that is bandwidth times log of 1 plus sigma to the base 2. So now how to find out the sigma? So the sigma should be found out or should be obtained using the average power constraint. Okay, so this average power constraint, what does it mean? Average power constraint says that, okay, we have discrete summation I equal to 1 to 5 P of gamma I by P bar should be equal to 1. And what is your P of gamma by P bar? It is simply sigma by gamma I. So summation I equal into probability. Yeah, sorry. So I equal to 1 to 5 sigma by gamma I into probability of gamma I should be equal to 1, which means that sigma, it's constant, it can come outside. I equal to 1 to 5 probability of gamma I by gamma I should be equal to 1. Therefore, summation I equal to 1 to 5, sorry, sigma should be equal to 1 over summation I equal to 1 to 5 probability of gamma I divided by gamma I, which is essentially 1 over expectation of your gammas, 1 over gammas. Okay, so now let us solve this. So therefore, sigma is basically equal to 1 over your expectation of your gamma i's. So let me again write it down here. Yeah, so this is what we have. So 1 over gamma 1 into probability of gamma 1. So that will be 0.3 upon 0.3162 plus you have probability of gamma 2, that is 0.5 divided by gamma 2, 1.2649, plus you have probability of gamma 3 upon your gamma 3, that is 0.1 divided by 7.9051, plus you have probability of gamma 4 divided by gamma 4, that is 71.1512, plus you have probability of gamma 5 divided by gamma 5, that is 126.4911. This denominator thing comes out to be equal to 1.3580 and this comes out to be equal to 0.7364. So therefore, your capacity with channel inversion comes out to be equal to your bandwidth, that is 40 kilohertz multiplied by log of 1 plus sigma, that is 0.7364, and this comes out to be equal to 40 kilohertz into 0.7961, which comes out to be equal to 31.844 kbps, which is much less than your ergodic capacity as well as your capacity with obviously the optimal power allocation. Is this clear? Any questions? Okay. So that's all I wanted to cover regarding the capacity part. Actually, that's not all. One or two questions are there more, but whatever related to your channel inversion, optimal power allocation for capacity, this is all I wanted to cover. Now I'll switch gears a little bit, and now I'll move on to the very basic questions of your SPED spectrum, and very basic because we obviously haven't gone into a greater detail of this CDMA thing, which we'll be basically covering in week 10. So just a very basic conceptual questions to understand the basic things. Okay. So the first question, or rather the question 5 here says that spread spectrum communication uses chips for the transmission and reception signals. You have a modulator with chip duration of 1.428 microseconds. So the first information given to us is the chip duration, that is TC, which is 1.428 microseconds, and you are transmitting a signal with symbol rate of 70 kilowatt. Symbol rate, it is 70 kilowatt. This is nothing but 70 symbols per second. So this is 70 symbols per second. Okay. So then what is your symbol duration? Okay, wait. You are transmitting a signal with symbol rate of 70 kilowatt. What is the spreading factor? So what we want, spreading factor Q, this is what. Now if I go back to the things that we have revised, yeah, here. So what we do, we divide the entire symbol duration into TC, into small time durations of length TC, which is your chip duration. And these are total. Okay, so what we do, we divide our total symbol duration into q numbers of small tc numbers of your symbol duration, chip durations. Okay, so this q into tc should satisfy, should be equal to your ts, that is symbol duration. So this equation should be satisfied. So essentially what we are doing is, this is one symbol duration, that is 0 to ts, and we are dividing it into tc, 2tc, 3tc, and so on till q minus 1 tc, and this is ts. So this is the first block, second, third, first chip duration, second chip duration, third chip duration, and then you have your qth chip duration. So therefore, the equation that we need to satisfy is q times tc should be equal to ts, where your ts is symbol duration. Okay, so now this q, sorry, this, yeah, this q is nothing but your ts by tc. Now based on the information given to us, this tc is given to us as 1.428 microseconds, and we want to find out the symbol duration, but we are given the symbol rate. So this ts, the symbol duration, is nothing but 1 over symbol rate is equal to 1 over 70 kilowatt, kilo symbols, that is into 10 raised to 3, and this comes out to be equal to, so I can multiply this by 10 raised to 6 and write it as microseconds. So this comes out to be equal to 14.28 microseconds. So therefore, this q comes out to be equal to ts, that is 14.28 microseconds, divided by tc, which is 1.428 microseconds. So this comes out to be equal to 10. So the q here comes out to be equal to 10. Is it clear? Any questions?
Ma'am, 1.428 is what?
Sorry,
Ma'am, 1.428 is what?
is the chip duration. It is given to us.
Okay, okay, ma'am. Okay.
Yeah. Any other questions? Okay, if not, then let me move on to the next question. Okay, so it says that where do you get the first null in the frequency domain representation of the spread sequence in question 5? So I'll again take you back to this thing here. Okay, so now what is given to us is this GC of t, which is basically this, and the pulse shaping filter that we are basically using is given by this GT, which is given to us here. Okay, so now it says that this pulse shaping filter, if you take its Fourier transform, then at what particular frequency do you get a null? Okay, so let us quickly do it. Okay, so the pulse shaping filter or pulse shaping signal is G of t, which is basically summation little q equal to 1 to capital Q into you have your C of q into GC of t minus q times Tc, and this GC of t is nothing but one over under root Ts for 0 less than or equal to t less than or equal to Tc. And we saw in the lecture that this thing has a Fourier transform of 1 over under root Ts into Tc sinc of f times Tc into e power minus j 2 pi f by Tc. Okay. So similarly, this Gc of t minus q times Tc will be basically having a Fourier transform of same thing, that is 1 over under root Ts Tc into sinc of f times Tc into e power minus j 2 pi f by Tc into e power minus j 2 pi f into q times Tc. Okay. So the first null is basically governed by what we look at is the magnitude and not anything else. Okay. So the first null is basically governed by this factor here. So the first null occurs at this quantity f times Tc when that is equal to 1. At f times Tc equal to 1, this is the property of the sinc function. So therefore your f should be equal to 1 over Tc. And 1 over Tc is basically, this Tc is what? This Tc, okay, so we have Q equals to Ts by Tc, which means that this Tc comes out to be equal to Ts by Q. So therefore this F is basically equal to Q by Ts. And this 1 over Ts is nothing but your symbol rate. So Q times symbol rate. And symbol rate is given to us as 70 kilosymbols per second, and Q comes out to be equal to 10. So this comes out to be equal to 700 kilohertz. Is it clear? Any questions? Okay. If there are no questions, then let me move on to the next question. Okay. So the question here says that consider two users simultaneously transmitting to a single receiver in an AWGN channel. Okay, so what is the situation? We have two transmitters. So this is transmitter 1 and this is transmitter 2. They both are transmitting to one receiver simultaneously. Okay, or we can also say that this is user 1, this is user 2. Okay, then this is a typical scenario in a cellular system with multiple users sending signals to a base station. So this can happen in a typical scenario. For example, two users are simultaneously calling to someone and it is connected to one particular base station. Okay, now this it says that assume that these two users have, this is not receiving, this transmit power, these two users are transmitting with power 5 milliwatt and 25 milliwatt. So this is an AWGN channel. So this user 1, yeah, add a page. User 1 is transmitting with power P1 equal to 5 milliwatt and user 2 is transmitting with power P2 which is 25 milliwatt. Okay, then what is given to us? Then they say that the total noise at the receiver in the bandwidth of our interest is 0.02 milliwatt. So the noise power Pn is what? 0.02 milliwatts. Okay. Then what they say, the channel bandwidth for each user is 40 megahertz. So bandwidth is 40 megahertz. Now they are saying कि suppose that the receiver decodes the user one's signal first. And while decoding this, the user two's signal acts as a noise What is the capacity of user 1's channel with this additional interference? Okay, so what are they saying? So they are saying, okay, so basically let us first set up what's happening. Let user 1 transmits x1 and user 2 transmits x2. So my receiver receives some signal y, which is x1 plus x2 plus n, where this n is my noise. So since we are simultaneously transmitting, both the users are simultaneously transmitting, we are going to receive a superposition of these two signals. So therefore your y received signal is basically your x1 plus x2 plus n. This is your AWG. So this is your additive white Gaussian noise. So what it is said here is, while decoding user 1's signal, user 2's signal acts as a noise. So first we are decoding user 1's signal. While doing this, we are treating user 2's signal as noise. And these are independent. X2 and Xn are independent. So the SINR for user 1's data, that is, let's say capital gamma 1, is given by the power with which the user 1 is transmitting divided by the interference that is coming due to user 2's transmission, which is basically the power with which user 2 transmits, plus your noise power, that is Pn. Now your P1 is what? P1 is given to us as 5 milliwatts. P2 is given to us as 25 milliwatt. And your noise power is given to us as 0.02 milliwatt. So this is basically 5 by 25.02. So this thing here comes out to be equal to 5 divided by 25.02. This is 0.1998. Okay, so now therefore the capacity for user 1, so that's what we wanted to find out, right? What is the capacity of user 1's channel with this additional interference? So capacity for this user 1 now becomes, that is, bandwidth into log of 1 plus gamma 1 to the base 2, which comes out to be equal to, bandwidth was 40 megahertz into log of 1 plus 0.1998 to the base 2. And this comes out to be equal to 10.5137 megabits per second. Now, so this was with interference, right? Now, what if we don't have interference? So, if interference was not present, then the SNR for user 1 comes out to be equal to gamma 1, let's say tilde, which is equal to, what was your transmit power? Your transmit power was basically 5 milliwatts. So 5 milliwatt divided by 0.02 milliwatt. So this comes out to be equal to 250. You see the difference. This was 0.1998 and this is 250. This is huge difference. This interference is killing the your SINR. It's just pulling down your SNR and hence pulling down your rate for user 1. So therefore, the capacity for user 1 without interference is given by bandwidth into log 1 plus gamma 1 tilde. This comes out to be equal to, your bandwidth is what? Bandwidth is 40 megahertz into log 1 plus 250. So this comes out to be equal to, just a minute. Yeah, so this comes out to be equal to 318.8617 megabits per second. And what were you getting? You were getting 10.5137 megabits per second, which is a very huge reduction in your data rate for user 1. Okay, now can we do better than this? We'll see if we can. But before that, let us see how the user 2 can be treated. So after decoding user 1, what happens is, while decoding user 2's data, it cancels user 1's data, let's say perfectly. And then then in that situation, what is the capacity of user 2? So what we had actually received, so receiver receives y equal to x1 plus x2 plus noise. Okay. Now what it does, first it decodes x1. So now your receiver knows x1. Let's say you need to assume it knows it perfectly. So now it knows it. So now if we want to decode your x2, we can subtract your x1 and then decode your x2. So now what it does, it creates y2, which is basically y minus x1, which is nothing but your x2 plus n, which is your signal, or basically this is what you will receive when there is no interference or only user 2 is transmitting. So in that situation, SNR for user 2, that is gamma 2, now becomes your P2 by Pn. Your transmit power for user 2 is given to us as 25 milliwatt divided by the noise power, that is 0.02 milliwatt. So this comes out to be equal to 1250. And for this, the capacity, that is C2, is basically 40 megahertz into log to the base 2 1 plus 1250. So this is log of 1250. So this comes out to be equal to 411.5546 megabits per second. Okay, so user 2 is getting fully benefited with this rate, with this approach, and it's getting its own proper capacity. But what is getting hit is your user 1. So there is a significant reduction in your user 1's data rate. Okay, now what we will do is, okay, so this particular calculation is telling us that user 2 is benefiting. There is no issue with user 2's capacity. User 1 is getting a bad rate. Now if we change this order, like if we first decode user 2 and then cancel its signal, and then you decode user 1, do we get little bit better data rate for both the users? Of course we'll be getting a hit on user 2's data, but is it that significant what we saw for user 2, user 1 in this particular question? So now what we want to do is, we want to consider the same scenario where we have a single receiver and two users are transmitting simultaneously to that particular receiver with the same powers which we have considered as 5 milliwatt and 25 milliwatt. So we have the same situation that we have a user 1 which is transmitting with 5 milliwatt, user 2 is transmitting with 25 milliwatt, and your noise power is 0.02. Your bandwidth is 40 megahertz. But now the receiver first decodes user 2's signal. So we have this y equal to x1 plus x2 plus noise. So what's happening here is the receiver is first decoding user 2's signal. And this is done assuming or treating the signal from user 1 or user 1's signal as noise. Okay, so therefore the SINR for user 2 is, let's say, gamma 2, and I'll write this as gamma 2 of 1, that is second, that is a new one. Let's, yeah, leave it. Yeah, so this will be P2 plus the interference power plus your noise power. Your P2 was 25 milliwatt, your P1 was 5 milliwatt, and your noise power was 0.02 milliwatt. So this comes out to be equal to 25 by 0.02. And this we have already seen. This comes out to be equal to 1250. Sorry. Oh, sorry. This is not 0.02. This is 5.02. So this comes out to be equal to 4.9801. So therefore, the capacity for this is, let's say, C2 for the first, for this particular thing, that is bandwidth into log 2 raised to 1 plus 4901. This is equal to 40 megahertz into log 2. Sorry, this comes out to be equal to 2.5802, and this comes out to be equal to 103.2066 megabits per second. So this is with interference, and capacity of user 2 without interference. This we had already seen in the previous one. This is exactly the same situation. So this comes out to be equal to 411.5546. So this thing here is basically approximately 1/4 of the capacity without interference. Similarly, here in the first one, in this first one, what we had was 318.8617 divided by 10. So here this rate was basically 1 by 32, approximately 1 by 32 of capacity without interference. So okay, here we are getting 1 by 1/4. There we were getting 1 by 32. The reduction was much higher. Okay, so something we are at some better place. Not too much, but yeah, we are at a better place here. We are getting a lower amount of hit when we are decoding this particular thing here. Now, what happens to user one's data? So while decoding user one's data, it cancels user two's data. So now we had or basically the receiver was receiving y equal to x1 plus x2 plus n. Now x2 is decoded. So receiver will cancel x2. So therefore we'll get y1 is equal to y minus x2, which comes out to be equal to x1 plus n. So therefore the SNR for this comes out to be equal to P1 by n, Pn. Now your P1 was 5 milliwatts and Pn was 0.02 milliwatt. And we had seen that this comes out to be equal to 250, and the capacity for this particular thing comes out to be equal to what? We have seen this earlier. It's exactly this quantity, that gamma 1 is 250, and the this thing comes out to be equal to 318.8617. So now here user 1's data rate is intact. It is not getting reduced at all. We are getting a satisfactory amount of data rate for the user 1, and for user 2 we are getting a hit in data rate, but this is 1/4. We are getting a reduction by 1 by 4th factor. However, when we were doing it in the other way round, we were doing the decoding in the opposite order or in the other order, we were getting a hit by a factor of 1 by 32, which was significantly high. So what it says here is, if you want to get hit for the capacity for every user, you decode the user with the highest power first, assuming the user with the lower powers as interferers, and then cancel out the signal or cancel out the decoded information from whatever you have received corresponding to the highest power signal, and then you can now you can decode your remaining low power signal. This is a very interesting technique, and this is known in literature. This is known as successive interference cancellation. This has been looked upon by researchers a lot. A simple concept that if you have superposition of signals, you first decode the signal with highest power, cancel it from the cancel it from the received signal, and then decode the remaining signals. So this is known as the decoding order. We start with highest power and then go on with the lowest ones. Is it okay? Any questions till this point? Okay, if there are no questions, then that's all I wanted to cover today. If you have any questions regarding anything that was covered in this week, feel free to ask. And if you don't have any questions, then you may leave the meeting. I'll be here for next 10 minutes or so. Thank you for attending today's session. And yeah, from the next week, that is week 10, week 11, and week 12, we'll have our lecture on the regular Friday timings.
Excuse me, madam.
Yes?
Hello,
Yeah.
madam. Is there algorithms to write the optimal power allocation, fixed power allocation like that?
Means optimal power allocation for capacity, we have seen water filling algorithm.
Uh,
I didn't understand your question.
okay, today I am presently working in NOMA technology, madam.
Huh.
Into NOMA technology to transmit the signals to the far user and also for near user.
Huh.
To transmit the signal with the highest power to the far user and lowest power to the near user.
Huh.
I want the analysis, madam, with the help of signal to noise ratio equations.
So these things you will have to dig up NOMA literature. So that is a
Yes.
like it will be there, but it is not something trivial that you will get something like a clean water filling kind of situation. So now you need to dig up the literature of NOMA. There will be many papers that do resource allocation for NOMA, I am pretty sure. So you will have to dig up. That is not something that I can cover in this lecture here.
Okay, madam. Thank you.
Yeah, yeah.